Subscribe to this channel and press the bell icon for more updates.
We shall continue our discussion about simple harmonic motion and waves from last two parts, where we discussed that periodic motions will be termed as simple harmonic motion provided the acceleration is proportional to displacement and acceleration and displacement are oppositely directed. We discussed the example of a simple pendulum. We also discussed that a particle moving in a circle does not execute SHM, but its projection on any of the diameter does execute SHM. Not only that, we also have discussed so far the velocity as is dependent upon the displacement, acceleration as is dependent upon the displacement, and also the energy conservation during the state of simple harmonic motion. It is very important to understand that the simple harmonic motion forms a very important and very integral part of various activities in our life. We have only discussed so far one example of simple harmonic motion, that is simple pendulum, but today I will give one more example. We can have number of examples on the subject, but just one more example will make you realize that we need to find out the restoring force and the mass, and we can find out the acceleration, and once we know the acceleration, which is proportional to displacement, through the relation of time period, we can find out the time period of such a motion. Let me take up one example. Let me consider a tube containing a liquid. Let us say this U tube contains liquid of density rho and height h. The area of this capillary is capital A, and the total height of the liquid in this capillary is 2h, as we can see. But just see, if a force is applied on one of the limbs and it rises to this, see, this will be depressed here, this will be raised here, and the total height to which it is raised, if this is h, this is h, is 2h. This height of 2h will exert the force on the remaining part of the liquid, on remaining liquid, and will make it move in this capillary. Let me find out the total force. For finding out the total force, I need mass of raised liquid which is volume into density, that is 2HA rho. This is mass of the liquid which will be moving the entire liquid. So the restoring force the force of the acceleration due to gravity is acting downward. So this is the restoring force for the liquid. And to find out the acceleration of the liquid, we definitely just have to divide this restoring force by the total mass. Mass of the liquid (2h A rho is the mass of the liquid, 2h is the total height of the liquid, A is the area of cross section and rho is the density. So this mass of the liquid is to be moved by this restoring force. So the acceleration can easily be obtained acceleration of moving liquid restoring force divided by moving liquid mass of liquid, that is 2HA rho G divided by 2HA rho. So can we see that everything gets cancelled? It is H rho Hg by capital H. This is acceleration. Acceleration and H is the displacement of the liquid. So we find acceleration proportional to displacement. This condition of SHM is satisfied. So we can now find out the time period of the motion of such a liquid. Time period. We have already obtained the formula that time period is equal to 2 pi displacement upon acceleration. It's 2 pi under root h upon 2h g upon capital H. Two pi capital H upon G is the time period. So this is the time period of the moving liquid in a capillary. Now, likewise, in every case where you find that there is a periodic motion and you just need to find out the restoring force of the moving body divided by the mass, and if it comes out to be satisfying the condition of simple harmonic motion, that is acceleration being proportional to displacement, we can apply this relation and we can find out the time period. Now, after this example, although we can take up more examples, but I would like you to try different examples and come up with your problems. Now let me just summarize as to what we have done and apply it for a very important aspect, that is waves. Before I come to the waves, let me just summarize to say that a particle, if it undergoes periodic motion satisfying two conditions of acceleration being proportional to displacement and the two are oppositely directed, this will be termed as simple harmonic motion. We have found out the time period of such a simple harmonic motion in simple pendulum case, in case of this liquid moving in a U tube. And as I said, we can take up more examples, but you need to try and come up with your questions. Now let's see. If you recall, I had discussed with you that although a particle moving in a circle does not execute SHM, yet its projection on any of the diameter does execute SHM. I had even found out the equation of motion of such a projected point on the circle. If this is a circle, this is the diameter, and here is a body which is moving, but this is the projected point, and the equation which we had obtained was A is the radius of the circle sine omega t, where omega is angular frequency of the moving particle. If you recall, we had also obtained the expression because the mean position and the initial position which I had discussed, I want to revise it again because that is going to form a very important component for the waves to be discussed. The initial position is the position when we start measuring or understanding the motion of the particle. That is called the initial position, that is from the time when we start observing. But the mean position would be the position of the particle in the absence of any kind of motion. So the initial position and the mean position could be same and may not be same. Look at in the first equation, the mean position is expected to be here, projected point, the particle, and the two are coinciding. And this is the equation for such a case where the mean position and the initial positions are coinciding. However, the initial position of the particle could be here. The initial position of the particle could be here. If it is here, that means it is already, equation would be y is equal to a sine omega t minus pi naught, because it is already on the downward direction, and this pi naught is called the initial phase. It could be on this side, that is above the mean position, and in that case the equation would be y is equal to a sine omega t plus phi naught. Right? So this is the equation, and then the word phase. Phase is one such parameter which measures two things, that is the position and the direction of motion of the particle. I want it to be emphasized once again that phase is that quantity, physical quantity, which measures the position as well as the direction of motion of the particle. How to measure phase is something we will discuss little later. Now I want to apply this knowledge for waves. I am talking of not electromagnetic waves, but I am talking of sound waves, or also known as mechanical waves. Look at the medium. Medium consists of particles. Let me just say the particles let's say the particles are arranged in a regular order like this. The first particle is made to vibrate. As the first particle made to vibrate, it passes on the vibration to the second particle by a process of induction. It need not be in physical contact, but by a process of physical induction, the vibrations of the first particle are passed on to the second particle. When the second particle starts moving, the second particle passes on the vibration to the third particle, third to the fourth, and so on. So the vibrations are passed on from particle to particle. And this also means if in the medium there are no particles, that is, there is a space, there is a vacuum. So if there is a space or the vacuum, there are no particles, so therefore such waves shall not be transferred or transmit it. But in the present case, when we are considering the particles being there, then imagine the first particle receives the vibrations from the source, passes on to the second, then to the third, then to fourth, and so on. It's like this. If I give a book to the first student who, without moving from his seat, just passes on the book to the second student without moving from his seat passes on the book to the third student, and after some time the book is passed on to the last student. So therefore the vibrations starting from first shall ultimately be passed on to the particle even at the last. The vibrations may as well be termed as energy. Therefore I can as well say that the energy is being transferred from particle to particle, and starting from first particle it can go up to the last particle. So this is how the energy is transferred, this is how the disturbance is transferred, and this transference of vibrations or energy or disturbance is known as wave. Finish?